Okay, are you getting something? Okay, okay. So, what? Remember roughly how this calculation went with getting the speed of light from watching the eclipses of Jupiter's moons. If the Earth was on the same side as the Sun as Jupiter, okay, we would see, the moon, okay, go behind Jupiter at a certain time. Okay, now we know, how fast these moons are traveling around, and so what the intervals between eclipses should be. But then when we try to predict it, say 6 months later, we find that we're a little bit off. Okay, the Earth is now, over here someplace, and turns out that the eclipse, we see the moon going behind Jupiter a little later than we expected. Well, what scientists realized was that that's because the light takes longer to get to the Earth when you're on the opposite side of the Sun. It has to go further. Now, how much further does it have to go? Well, it has to go the diameter of the Earth's orbit further. Yes?
Wait, so Jupiter stays in that same spot when the Earth is rotating? Or doesn't,
Oh, well, pretty much. I mean, it takes Jupiter like 12 years or something to go around, so it's only moved a little bit. I mean, right. There's going to be a time when the Earth is, when again, Jupiter and the Sun and the Earth are pretty much lined up. It's actually going to be when the Earth is over here. Okay. But anyway, it's the time delay basically between when you expected to see this eclipse and when you actually see it is the time, the extra time that it takes the light to go the diameter of the Earth's orbit. And so by working that out, scientists came up with an estimate for what the speed of light was. Now, they were a little bit off, actually. You can see this is kind of a tricky calculation because you have to be able to predict the times of these eclipses really accurately. It only takes, in fact, does anybody remember? I think I told you once how long it takes light to go the diameter of the Earth's orbit. Daniel? Oh, no, you're thinking of Nick? Yeah, 16 minutes. Nick remembered the number. So now, that's not a big time period. I mean, you have to be able to predict these eclipses really accurately. I mean, within a minute or two, in order to get any accurate value for the speed of light here. And back in the 17th century, when this was done, people didn't have quite that accurate predictions for the eclipses. So, in fact, what they ended up getting, the estimate for the speed of light that they got was, let's see, estimated speed of light that came out of this calculation was about 140,000 miles per second. Which turns out to be a little low. Now, remember that who made the first attempt to measure the speed of light? Daniel?
Galileo.
Yeah, it was Galileo. That was his. He had this idea of not using, astronomy, but actually just doing it with lanterns with a friend of his, that they would be a mile or so apart and just try to measure how long it took light to go from one guy to the other, stand on different hills and with lanterns. Now, that didn't work too well because the time, of course, was too short. But people didn't give up on the idea of actually doing an earthly measurement of the speed of light. And that's what I want to tell you about this morning, the first guy who actually did it. So all that was review. And we have this very challenging problem of measuring a really short time interval because light goes so fast. And the guy who first figured out how to do that was a French guy, Louis Fizeau. I think that's how you pronounce that. And he did this in 1849. Now, let me just describe what his setup was here. I mean, he basically went back to Galileo's idea. Stand on different have light go between hilltops and try to measure the speed. But he does it a little differently than Galileo. He doesn't actually even use a friend. He's going to do this all by himself. So what he does is put a mirror on the other hilltop. Okay, so his basic setup here is he's got a all right. Wow. They didn't have light bulbs at this time, but he's got some light source here. Okay. And he's got what's called a half mirror here, so half the light that hits it will bounce off and half will go through. Okay, it's called a half silvered mirror. So basically the mirror coating is so thin that it only reflects about half the light, and it lets half the light through. Okay, so the light coming from this light source is going to hit this mirror, half mirror. Some of it's going to bounce off and go a long ways to another mirror. Now, when the light bounces off this mirror, it's going to bounce right back, right? Some of it is going to go through this. Half of it is going to go through this half mirror here. The rest is just going to be reflected right back down to the light source, right? Now, Louis is watching from over here. This is Louis's eye. Now, I haven't told you the clever part yet. Okay, how is he going to time this? Well, he's got an idea. He has a wheel that has all these teeth in it at regular intervals. Okay, you get the idea all the way around. And he is going to put, oh, did somebody ask? Okay. He's going to put that wheel right in the light path here. I mean, where, so the teeth are in the path of the light. So when the wheel is oriented so that the light path goes through one of these gaps, okay, then Louis actually sees the light beam, right? But when a tooth is in the way, he doesn't see it. Yeah.
How far away was that thing, whatever it is?
Oh, well, it turns out not to matter. I mean, it was real close to this. I mean, well, Louis has to be able to manipulate this thing. I haven't told you the whole story yet. So this is close to him. Now, this mirror over here is about, in his experiment, was about 5.5 miles away. Okay, the rest of this equipment is right next to Louis. Okay, now here's the idea. He figures that, I mean, he looks through here. I mean, let's say he's the light is going through a gap here. Okay, he looks through and he sees the light. What happens when he starts this wheel spinning? He starts spinning it. Well, he'll still, as long as the outgoing beam can get through a gap, and then on the way back get through a gap, you know, he'll see the beam, right? But his idea is there should be a speed of this wheel that the outgoing beam goes through a gap, but when it tries to come back, okay, when it's on the way back, the gap has a tooth has now moved into the gap, okay, and it's blocked. So every outgoing beam will be blocked on the way back by the next tooth. In other words, the wheel has turned just enough as the light that goes out, when it tries to come back, say it went out through, say, this gap here. By the time it comes back, the wheel's turned just enough so a tooth is now in that gap, and it blocks it. Now, if you find that right speed of the wheel, then the image of the light source should disappear, because every light that makes it out will be blocked on the way back. Yes?
Wait, so how did he, like, keep a constant speed the speed? Was it just turning with his hand, or did he have like a motor or something?
Oh, that's a good question. Unfortunately, it's a good question I don't know the answer to. The book that I have that describes his experiment doesn't go into that detail. I wondered about that myself. You know, exactly, because he has to know that the wheel is being turned at constant speed. So I suspect he did use some kind of motor that would keep the speed constant. Yeah, you couldn't really do this and just turn it by hand, because if you wouldn't know whether you were always turning it at the same speed. Okay, so does everybody get the idea here that there should be a speed of this wheel where every outgoing light beam that makes it through a gap will be blocked on the way back because the wheel has moved just a little bit and there's a tooth in that gap now. And if you get that speed right, you shouldn't see any light source at all. Okay, so, well, Louis Fizeau actually does this, and he finds that, let me see, I'll give you his data. He used a wheel has with 720 teeth, and here's his experimental result. Light is blocked when wheel is turned at 12 revolutions per second.
You have to spin it 12 times around.
12 times per second. So you have to spin it fast in order for the image of this light source to disappear, so he can't see it. So what he does is he starts out spinning it more slowly, and then he just cranks up the speed until the image of this light source disappears. And it disappears when he gets to 12 revolutions per second. Now you've got all the information you need to figure out the speed of light. I should just leave that as an exercise, I guess. Well, I guess we've got time to do it. But let me. Okay, everybody knows the setup now, right? Well, how would you start to figure out what the speed of light has to be now? Nee.
Find out how long it takes to get between two teeth on the wheel.
Yeah, exactly, because that's the key question now, because we know that, first let's do the easy part. Okay, speed is equal to distance over the time interval, right? Okay, what's the distance here? 5.5 miles one way, right? Yeah, it's 11 miles that the light is actually traveling, because it has to go there and back.
But how do you get a strong enough beam to actually travel that?
Oh, well, if you have a bright light source here, actually, it's not the beam strength that's tricky here. It's orienting the mirror. so that it bounces right back along this path. Because obviously, even a minuscule misorientation of this mirror will send the light back, so it, misses. It doesn't go back exactly in the same direction. That's the tricky part. But if you get this mirror in the right orientation, and you you have a reasonably bright light source and a clear day, there's no problem with the intensity, because you're not really losing light here. I mean, light just goes in straight lines and comes back.
Okay, so you can like use a regular flashlight.
Yeah, right. Right. Okay. Yes, Daniel.
Just a quick question. How do you know the equation of speed equals distance over time?
Oh, well, I mean, that's the definition of speed, right? How much, we talk about speed as like miles per second, right?
All right, gotcha.
Or miles an hour. It's how much distance you've covered in the time interval. That tells you how fast you're going. So now, but the distance in this case is the easy part, right? So we know that's 11 miles because we're talking about a round trip, and the one way is 5.5. So the tricky part, as Neve said, is the time interval, figuring out the time interval. Okay, so we know speed in this case is 11 miles over time interval. Now, what's the time? Well, if the wheel went all the way around once, okay, how long does that take? Neve? 1/12 of a second, right? It goes around 12 times in 1 second. So time equals 1/12 of a second in order to go all the way around. Now, it hasn't gone all the way around, right? How far around has it gone? Neve?
1/720th.
It's a good guess. Let's write that down. 1/720th. Is that right? Almost is the answer. But one thing is being neglected. It has 720 teeth, right? Right. Yeah, it's because you're only going to get the light blocked. Remember, you're only going from a gap to the adjacent tooth. You're not going from one tooth to the other. So you're going half that distance. Okay? So now you can see that's a pretty short time interval. So let's finish doing the math now. Now the rest of it's easy, right? Okay, so speed equals, well, 11 Okay, that's the miles. Now, we're dividing that by that number, right? Okay, so math wizards, what's the first thing you would do here? Neve?
Put all the denominators on the numerator.
Right, because we can multiply numerator and denominator by the same factor without changing anything, right? So if we multiply top and bottom by 12, okay, we get rid of this 1/12, and we put the 12 up here. And we can do that for the other two numbers. So now we get that. And remember, we're working in units of miles per second. So everybody can do that in their head, right?
I think it's 190,080.
Let's see, I think maybe I dropped the 80, but I have 190,000 in my notes. Let's just do that. You might be right about that 80. I tend to round off. Okay. That is, that's amazing. Right? I mean, that's a very clever way to measure the speed of light, which is a very tricky thing to measure, obviously, because you're working with a really small time interval. So, I mean, this is, what, about a, I mean, it's much less than a 10,000th of a second. Yeah, right, 1/16,000th of a second. So that's a really short time interval. But what you need is to, but if you're clever, like Louis Fizeau was, you can come up with a way of, in effect, measuring such a short time interval and getting roughly the right number for the speed of light. I mean, this was the first time that people had a value of the speed of light that was good to better than 5%. You know, they were off by 25% in their initial calculation of the speed of light from using the moons of Jupiter. Yeah, Ben.
Now do we know exactly how fast the speed of light?
Oh yeah, we know exactly now. I mean, the modern techniques for measuring the speed of light are extremely accurate. And in fact, let's see, I'm sure that this book that I have here has the speed of light out to God knows how many significant digits. Let me see. Well, I'll look it up later, but I know, I mean, the real number is 186, you know, something. So it's 186,000 miles per second, but I'm sure that, I mean, these numbers aren't zeros, these last three. I just don't know it after 186. But physicists know it out to probably 10 numbers today. But this was a very good value for 1849. and a lot better than the previous value based on the moons of Jupiter. So that was an important advance. So now we not only know that light is a wave, somewhat like sound is a wave, but we know how fast it travels. Rather than 350 meters per second, we've got 190,000 miles per second. Okay, now the sound is a wave, light is a wave. We know the speed of both now, but are they the same kind of wave? It turns out that with a little bit of thought, you can see that there can be different kinds of waves. A wave is just a periodic motion of something, right? But that motion can happen in different directions. Now, so let me, you can call this next section, I can start out calling it types of waves. And let me give you two examples of how of very different periodic motions that are both waves, but different kinds of waves. So let's call the first one, does everybody know what a slinky is? Okay. This is a slinky wave. Okay, let's say you have a slinky hanging down to the ground, and you decide to stretch it and compress it. So you start doing this motion with it. Okay? So okay, now what you're going to do if you do that, you'll create little, compression waves, basically, in this slinky, right? There'll be parts of the slinky where the turns are close to each other and parts where they're stretched out. And you'll be able to see those parts where the slinky's compressed sort of moving down the slinky. Now, any given part of the slinky, if you look at the motion of any particular turn of this slinky, the motion is in the up and down direction, right? It's just doing this. Okay? Now, you can think of that, that is a wave, right? It's a periodic motion of each part of the slinky. And when you look at the slinky, you'll see places where it's like stretched out, and places where it's bunched up, and then stretched out, and bunched up. And those compressed parts will move down the length of the slinky. Now, So we have a wave in this case where the vibratory motion of the parts, okay, that motion is in the same direction as the propagation of the wave, right? So this is called a longitudinal wave. And what that means is that the vibrating motion is along the direction of the wave. Now this will become clearer if we contrast it with an opposite kind of wave. So let's do a rope wave, okay, where we have a rope, okay, stretched horizontally, and we take an end and shake it up and down. Okay, what's going to happen? You're going to have like these wave pulses going in the rope that travel down the length of the rope, right? Now here, if you look at any part of the rope, what is the direction of the motion of that segment of the rope? Ben? Well, is this section of rope here actually moving in that direction?
Going up and down.
Yeah. This little section of rope here, if you confine yourself to a given piece of the rope, is actually moving up and down. I mean, when a crest hits this piece, it's moving up, right? When a trough hits that piece, it moves down. Okay, but the wave itself, the wave pulse, if we look at it, is moving down the length of the rope, right? So the wave is in this direction, down the length of the rope. The actual motion of any piece of rope is in a perpendicular direction. It's up and down. Okay? So this is called a transverse wave. You'll see why all this is important in a minute. But you need to have this basic distinction between the two wave types before I can tell you what physicists discovered about light and sound. Okay. So, I mean, it's called a transverse wave for the obvious reason, right? That the actual vibratory motion in this case is in the direction transverse to the direction of the wave propagation. Whereas here it was along the wave propagation. Okay, we'll pick this up this afternoon.